Hi, this is John Gardner, Professor of Mechanical and Biomedical Engineering at Boise State University, and welcome back to Module 2 of Industrial Energy Efficiency Process Cooling. This is the second part of Module 2. We started by introducing the thermodynamics of vapor compression cycle, and we're going to continue looking at a specific example. So, as you recall, where we ended the last lecture is we pulled up a typical window air conditioning unit that you could buy at Home Depot or Lowe's or Sears, and it's the General Electric AEW 10AQ, and it's rated at 10,150 BTUs, has R410A refrigerant, and has an EER of 10.8. So what do those specifications mean? Well, 10,150 BTUs doesn't make any sense unless you've got some kind of time associated with it, and in fact all these commercial units say they have the ratings in BTU, but it's really BTU per hour. So it's 10,150 BTUs per hour. The EER is a statement of the coefficient of performance. We talked about that earlier, but it's not a dimensionless parameter in this case. It is the ratio of BTUs removed from the conditioned space to the watts consumed. So the ratio it's either ratio of BTUs per hour per watts or ratio of BTUs per watt hours. It gets the same thing. The units of EER are BTUs per watt hour. This is 10.8 is the rating for this unit. That can be converted to the coefficient of performance if we know that there's 3.412 BTUs in a watt hour, so that means our coefficient of performance is 3.16. Okay, so the only way we can really get any traction on here is start making some assumptions. I mean, if we had the unit, we could start making some measurements. We could see how hot the condenser unit was, how cold the evaporator units are. But we know it has to be. We know that the condenser has to be higher and above ambient. So let's just say it's a really hot day and maybe it's 100 degrees. So the condenser is at 120. And we know it's pretty cold air coming out of these units, right? So I don't think it's too far off to guess that the condenser might be running as low as 50 degrees Fahrenheit. So with just those two numbers, we can start doing some analysis. So in the analysis of cycles, it helps to build a table. And it also helps to have the TS or pH diagram in front of you. Some diagram, some representation of how the cycle moves around. For example, we can look at this and say, hey, the inlet of the compressor, state 1, is at saturated vapor. We've made that assumption. We'll release that assumption in a bit, but right now we're saying it's saturated vapor, which means we know its quality, and we have the quality of 1 in state 1. So we put that in the table. We also know some temperatures, right? We know the temperatures of 1 and 4. They're at 50 degrees. So we'll put those in the table. We know the temperature of the condenser is 120. We don't know the superheat, but at least we know the value for state 3 is 120. And speaking of state 3, we know it's at the saturation line. So its property, its quality is pure saturated liquid, so it's a quality of 0. So before we even get started, we've got all this information here. And we might as well finish out state 2, and we know that's in superheat. So we begin with just a kind of a educated guess about some temperatures, and we've got a start on the table. Okay, so now we have to turn to the thermodynamics. And on line states 1 and states 3, we have two independent properties, right? We have the temperature and quality of both of those. So we can fill those in. And let's go ahead and do that. We turn to the tables or whatever way we have of looking up our thermodynamic properties. So we find the pressures of 1 and 3. Those are also the saturation pressures associated with those temperatures of the refrigerant. We can look up the enthalpies, we look up the entropies, and we've got to start here. So now what else do we know? Well, for example, we know 2 and 3 are lying on the same isobar, so their pressures are the same. So we can just copy whatever pressure we had from 3 into state 2. So what else do we know? We know the expansion through the valve, or the expansion valve, is isenthalpic. That means the enthalpy on both sides are the same. That means the enthalpy at 4 is the same at the enthalpy at 3. So we can just copy that value of 61.7 down into for property 4. And finally, as I mentioned in the last slide, the compression is isentropic, meaning that the entropy at state 2 is the same as the entropy at state 1. And so we can just copy those over. So pretty straightforward. We can go to the next slide and say, okay, we've got all these things copied in, and now in every one of these rows we have 2 independent values, right? So so we can fill in the states. The only thing we're really missing, and what we truly need, is the enthalpy at state 2. And let's find the temperature there too, right? But we have the pressure, we have the entropy, and we know it's in the superheat region. So we've got more than enough information to find it all. So in finding the values for state 2, it gets to be challenging because the tables in the superheat region tend to be kind of sparse, and they're not really arranged in a way to make it easy to find that. Usually requires some double interpolation. So here's a shot of the superheat tables for the refrigerant 410A, and we can see here we're trying to find entries that line up with our entropy. So the entropy is 0.2459. We know that from the tables previously, and that's the same entropy that we found for state 1. And we know the pressure. We know the pressure is 431. So we find the superheat tables organized by pressure. So we have a column associated with 400 and a column associated with 450. So we have to interpolate between those two. But before we even do that, we have to, go in there and find the entropy values. So under the, say on the right, under the 450 value, the pressure of 450, we find the entropy that we're looking for lies somewhere between 150 and 160 degrees Fahrenheit. Closer to 150, right? Because it's just a little bit higher than that 0.2448. And then on the 400 side, we have the entropy we're looking for lies between 130 and 140 degrees Fahrenheit, closer to 140. So we have to interpolate between those two, find a temperature between 130 and 140 at 400 psi, and that's associated with our known entropy, and then find another temperature between 150 and 160 that corresponds to the known entropy at 450 psi, and then interpolate between those two temperatures between 400 and 450 to the known pressure of 431. Kind of confusing, but it's the kind of thing that makes more sense once you do it. And as we like to say, we will leave the intermediate steps as an exercise for the student. And suffice to say, I found the temperature. Remember I said it was going to be around 150. It's 147.6 Fahrenheit. And the enthalpy is 133. And now we can solve the problem. And I would encourage you to do that. And in fact, that's the problem sets for this module builds on this, right? So the first problem in the problem set is to complete the thermodynamic analysis. Find the COP, find the compressor work, find the mass flow rate, but to do that we have to know something that's not just intensive properties, right? We need to know something from the outside, and we do. We can assume the specifications for its refrigeration capacity is correct, which is 10,150 BTUs per hour. So once you know that, doing an energy balance around the evaporator, you've got H1, you've got H4, you can find the mass flow rate. And once you have the mass flow rate, you can find everything else. You can find coefficient of performance, you can find the compressor work, anything you need to know. And so we can compare those results to what we have, particularly the EER, and postulate on the how it might change. So tables are great. We've all learned how to use them, but in the modern era there are other opportunities here. I found this website, kind of a web thermodynamic lookup engine. It's by the University of Wisconsin. It's a refrigeration research center. They do nice work there. This one is okay. I have found it to be not terribly accurate, but for the purposes of homeworks, that'll be fine. I've also found a great add-on to MATLAB called Cool Props. And if you don't have that available at your installation, I encourage you to look into that. And there's also an add-in to Excel spreadsheet that gives you functional calls to get thermodynamic properties. So they're all available to you. My caveat is don't mix. In other words, if you're using one source for thermodynamic properties, do everything from that. And the reason is things like enthalpy and entropy are always established relative to some reference point, and not everyone uses the same reference point. So if you try to mix your sources, you're likely to come up with some errors. Good way to verify whether they're using the same reference point is just find the same enthalpy and entropy at from the two different sources. Make sure you get the same number. Okay, just a little bit more, and then we'll wrap this up. So we assumed that the state at the inlet of the compressor, the suction of the compressor, was pure vapor, saturated vapor. And it needs to be vapor, or the compressor could run into trouble, right? We don't like liquid, which is generally incompressible in a compressor. It tends to give it all sorts of heartache. And so what we usually do is we usually control these systems to they control the refrigerant flow through the evaporator in such a way that it's always a little bit into the superheat region. So, and this is usually done with a thermal expansion valve, and the thermal expansion valve is a valve that uses refrigerant pressure to modulate it, open and close it a little bit, and that refrigerant is heated or cooled at the outlet of the evaporator. So there's usually a little copper bulb that's closely attached to the pipe at the exit of the evaporator, between the evaporator and the compressor, and a thin copper tube that runs back to the thermal expansion valve. And so it just by measuring the temperature, by sensing the temperature there, it puts that refrigerant in different states, changes the pressure in it, and can open and close the valve. And so we can dial that in to a certain number of, we call it degrees of superheat. So it's usually something like 5 to 10 degrees of superheat. That assures that you've always got you always got vapor going into the compressor, that you don't have chunks of fluid going in there. So if it gets too cold and it's not all evaporating, then the fluid then there might be fluid in the compressor, so it decreases the refrigerant flow, giving it more time to evaporate. If it's too hot in there, the condenser gets less efficient. It increases the flow to make it work a little easier. So it's a pretty neat system. It's been around for a long time, and it's in a very large number of systems out there. We'll see other components in between here. There's small cylinders called receivers that basically allow for some separation. So if there is some vapor or liquid mixture, it lets the liquid settle out and evaporate slowly. Sometimes you'll see sight glasses so you can see whether things are in liquid phase or not. Oil separators are common in the bigger systems because the oil gets entrained in the refrigerant, particularly for screw compressors. So we'll see all those things as we get out there. Right now we're looking at a residential unit with a typical condenser, which looks like a radiator in a car. Big bunch of tubes with fins and a fan that blows air across it. We saw other things in Module 1, cooling towers and evaporative condensers, which get a lot more interesting and can be much more effective. They're tied to the wet bulb temperature and can be very interesting and can also be very confusing. So we'll spend some time talking about those. So we'll establish this trade-off between compressor discharge pressure and its work it provides and the cooling tower capacity. But that's getting a little ahead of ourselves. That's in Module 4. So it'll be a while yet. So that's it. We can use the thermodynamics from our undergraduate thermal class to analyze these things. We have to make some assumptions or some measurements. So if we're on site, if we're actually looking at it, it'd be great to know the pressures of the evaporator. And usually the best thing to do is just look at the suction and discharge pressures of a compressor. So big refrigerant systems usually have gauges there. That's the best data. Short of that, we can find the temperatures of the evaporator and condenser. And keep in mind that's the temperature at the outside of the tube. Since there's heat transfer across the tube wall, we know that there will have to be some kind of dT dx that's going on there. So that's a little confusing. We have to do a little fast footwork to somehow compensate for that. And just one last thing, it's really hard to know mass flow rate. Mass flow rate meters are expensive. They're kind of fussy. and so we don't generally use them in industrial settings. And yet this would be probably the most useful piece of information. So anything we can do to kind of deduce mass flow rate is very valuable. So that's it. That's the end of Module 2, and good luck with the problem set and the quiz, and we'll look for you on the discussion boards.